All objects, living or not, emit infrared radiation as a function of their absolute temperature. A PIR, that's passive infrared motion sensor, detects the infrared radiation of an intruder up to no good in your house. The sensor responds to infrared radiation centered around a wavelength of 10 microns, the wavelength corresponding to the average skin temperature of 93 degrees F, that's 34 degrees C. In practice, most sensors will respond to wavelengths between 4 and 20 microns. The Fresnel lens concentrates the IR energy on the front face of the sensor housing. The IR sensor is housed in a hermetically sealed metal can to improve electrical noise immunity and provide a more stable temperature and humidity environment. The window of the can is made of IR transmissive material, typically coated silicon, that protects the sensing element inside. A pyroelectric sensing element generates electric charge in response to thermal energy flowing through it. The plate has two deposited electrodes, one on the front side and the other on the back side. Infrared radiation absorbed by the front electrode causes the upper side temperature T sub S to increase over the base temperature T sub A. The front side expands, causing mechanical stress in the internal crystal. In turn, the stress leads to a piezoelectric charge inside the crystal. Recall that many pyroelectric elements are also piezoelectric, which is required for a PIR detector. The induced charge creates an output voltage. The very small voltage of the detector is amplified and sent to a comparator to determine if it exceeds the threshold that identifies an intruder. The focusing lens creates an upside-down image of the room on a focal plane where the light-sensitive element is positioned. Recall from freshman physics ray diagrams that a refracting lens always reverses the real image on the focal plane. When the room is unoccupied, the image is static and the output signal from the element is non-zero, but stable. Being at room temperature, they emit less energy per unit area than warm-blooded living creatures. If the burglar enters the room, his image appears on the focal plane of the detector. Eventually, his image will overlap with the sensing element. If he keeps moving, it eventually will not overlap. Detection is based on the change produced between the image coinciding or not coinciding with the sensing element. This leads to the change in infrared energy and the resulting transfer of heat energy through the pyroelectric element. A negative analog voltage means that the intruder is moving in the opposite direction from that of a positive voltage. The comparator converts the analog voltage output into two logic levels: 0 if no motion detected, and a 1 if motion is detected. The frequency of the square wave for the digital output is proportional to how fast the intruder is moving. The piezoelectric properties of the PIR element have a negative side effect. If the sensor is subjected to mechanical stress due to loud sounds or structural vibrations, it may generate a spurious charge indistinguishable from that caused by infrared energy. Your motion sensor could generate a false alarm. The police could come to your house and think you are the cat burglar instead of Oliver. Then you could spend the night in jail, which would not be fun. In order to prevent false alarms, a passive IR detector is usually fabricated as a differential detector, per the diagram on the right. Two identical sensing elements are positioned inside the sensor's housing. Two slots are provided in the cover of the metal can, as shown on the left diagram, so that the approaching burglar, feline or human, is seen sequentially by the two sensors. The elements are connected to the interface circuit so that they produce out-of-phase signals when subjected to the same in-phase inputs. The differential design works in this way. When spurious signals due to mechanical stress are applied to both sensing elements simultaneously, They are canceled at the input of the electronic circuit. Because the infrared energy focused by the Fresnel lens is absorbed by only one element at a time, the cancellation is avoided. Thus, only the infrared energy is used to detect presence of the object, not the spurious signals. A differential PIR detector is fabricated by applying two pairs of electrodes on both sides of a single plate. Each pair forms a capacitor that may be charged either by heat or by a mechanical stress. The electrodes on the upper side of the sensor are connected together, forming one continuous electrode. The two bottom electrodes are separated, creating two opposite serially connected capacitors. Depending on the side where the electrodes are positioned, the output signal will have either a positive or negative polarity for a thermally induced response. When the burglar passes slot 1 of the detector, capacitor C1 charges, creating a voltage greater than the threshold window. The JFET transistor is used as an impedance converter and a voltage follower. This triggers a signal that the burglar has been detected. Presumably, the burglar continues past slot 2, particularly if he thinks he's headed to where the cash and jewelry is located. Then capacitor C2 charges, generating a voltage of the opposite polarity. A second signal is sent that the burglar has been detected. When the thermal image moves from one electrode to another, the current I flowing from the sensing element to the bias resistor R changes. It goes from 0 to positive, then back to 0, then to negative, and again back to 0. The resistance R must be very high, on the order of 10 gigaohms. Alternate current of only 1 picoamp is typically generated by the element in response to the burglar. Using a 10 gigaohm resistor, you still only get a 10 millivolt output voltage. Once the alarm system triggers, the burglar is in for a rude awakening. Depending on what system you have, the burglar's ears will be crushed by a loud siren and perhaps a rude message stating, "Leave the house immediately. The police will be called." Assuming the system is not bluffing, the alarm company calls your local police department, who in turn should visit your house looking for burglars. Hopefully, the police will not mind your 140-pound dog. Commercial PIR motion detectors come with a variety of features. This model is temperature compensated from minus 10 degrees C to 55 degrees C. It performs in high humidity environments as long as you don't get it soaking wet. It is installed in areas where people routinely use their cell phones, so it is designed for RF immunity. I didn't find details about the shock algorithm, but I assume this refers to our discussion on the differential detector. You choose low sensitivity if you want to make sure the unit doesn't create false alarms when your pets pass by. Installers mount the sensor high enough on the wall so the lens sees mostly people, not pets. I suppose a burglar could slither on the ground to avoid detection by the motion sensor. However, he would need to know in advance exactly where the sensor is. And if he knows that much about your house, he probably also knows how to disable the alarm system. In motion detectors meant to survey a large area or an entire room, the detector uses a faceted infrared Fresnel lens. The lens is divided into arrays of smaller lenses called facets. Each facet works as an individual lens, creating its own image on a common focal plane. More about how that works shortly. The detectors are sometimes mounted on the ceiling in the middle of the room, forming predetermined detection zones. Ceiling detectors are commonly used in commercial establishments, such as for a museum stocked with priceless art or a bank with lots of cash. In these detectors, the sensor should have an even number of pairs of electrodes oriented symmetrically in order to reject the in-phase signals. The commercial detector shown here has the zones fanning out at up to a 36-foot, that's 11-meter radius from the center of the room that is up to 12 feet high, which is 3.9 meters high. The center zone looks down at the center of the room, with zones B, C, and D looking for motion at successively larger distances from the center. With this design, even the Mission Impossible team would have a difficult time suspending themselves from the ceiling of a room to steal secrets from the bad guys. Of course, in the movies, they never get caught. Shown in this photo is an application for a ceiling mount PIR sensor. Two of these sensors are mounted on the ceiling of a room full of paintings at the Museum of Modern Art in New York City. Each of these sensors protects roughly half the room. The ceiling in this room is roughly 12 feet high, which is 3.66 meters. I can't tell you exactly how high, as the security guard in the room would never have let me measure the actual distance. The PIR sensors scan the room for burglars after the museum is closed every day. Supposedly, this modern art in the room is priceless, or at least sold at auction for prices that neither you or I could afford. However, if you look at the paintings shown in the lower right corner, I'm not sure that they'd be worth it. An infrared faceted Fresnel lens is divided into a series of smaller lenses called facets, per the photo in the upper left corner. Each facet points towards a different part of the field of view, but all facets get focused on the same plane. This is another case of engineers copying nature. You probably know from personal experience it is difficult to swat a fly. These insects have faceted lenses, and they can see you coming from far away. The facets form multiple images as shown in the upper right corner of the slide. When the object moves, all images move across the focal plane simultaneously. At least one of these images will be detected by the sensor. The image in the lower right corner shows a typical field of view. The gray shaded area indicates where an image would be detected. The white area shows where it would not be detected. Of course, the width of a person is greater than the width of the white area. The detector will always find the burglar. The broader issue is whether the burglar knows how to disable the alarm system before he enters the house. In that case, he won't care if the motion detector senses him. To determine the focal length of any single facet of the lens, you use the formula F equals LD divided by delta. We're using the diagram in the upper right corner. D equals the width of the sensing element, L equals the distance of the object from the lens, and delta equals the minimum displacement of the object. Then the facet pitch P is given by P equals 2ND, where D equals the width of sensing element and N equals the number of facets. Let's recap. This wraps up our discussion on PIR motion detectors. Now we're going to talk about ultrasonic detectors.